Okay, so the static, where we're not able to move the object, it's not moving at all. Sliding, where you do get it to move. Sometimes you can get it to move, with just a push, and then it kind of goes for a little bit and then stops. Or if you're continuing to apply the force the whole time, then obviously it'll continue to move the whole time as you have that force applied. And then the final one we had is the rolling friction. And we showed that yesterday with the straws, right, where I can give it a small shove and it's going to go a lot longer and farther than if I just had it on the tabletop, because you have all that surface area that's in contact, causing that friction, or just those 6 individual lines on each straw where, it's in contact with the table. So 6 lines versus an entire surface area makes the difference. Okay, so the rolling is a huge part of this. It said that the normal force yesterday, go ahead and close up your Chromebook there, Don. That the normal force is probably the most confusing, I think. 3 main things between the solid and the solid. It has to be something that is in contact, and it has to work perpendicular to the surface. So again, if my surface is horizontal, gravity's pulling down, but my normal force is pushing up, right? And so it's the pushing up that I think sometimes is hard for us, because we're like, really? Like the floor is pushing up on me, or the seat's pushing up on my legs and my buttocks as you're sitting in the seats? It's like, that doesn't seem right. But it is. It's pushing you up to keep you from being pulled all the way through or down more. So the idea that if you are on a slanted surface, like if you're like this, my normal force is going to just follow the surface, and it is going to be perpendicular at all times. So it forms that 90-degree angle. So if you're forming, if this is my normal force, it would be, if I'm at an angle, gravity is not perfectly canceled out. If this is the downward force of gravity and this is the upward normal force, this would be canceled. Those are opposite directions. One's going down, one's going up. But if you have it like this or like this, right, those forces don't cancel out. And if they don't cancel out, then it's going to feel like gravity is stronger and it's pulling that object down the ramp or down the hill. Yes?
Look at this.
Yep, exactly. So the normal force.
So gravity makes it go faster.
Right. And the thing is that when it's flat, you don't expect that pencil to move. It's going to stay right there, right?
Flat, but then once it's like that, it moves.
And then what's going to eventually stop it?
Gravity itself.
Nope, friction.
Friction.
Friction, yep. So when it's just sitting there with no force applied, you don't expect it to move. But just like the picture, let me back up a second. Oh, too far. If he lets go, when he's pushing this crate up the ramp, what's going to happen to the crate? It's going to slide back down, right? We understand, possibly, hopefully not. But if this was on a flat surface, so just like my book, do I expect my book to slide off the table? No, but if I would tip this table up and I would get it so it's at an angle, then just like Dylan's pencil rolling down his eraser, we would expect that book to slide right off, okay? So, and that all is because of the normal force. It's no longer canceled out by gravity, right? There isn't enough of the normal force. Because it's at that angle, it's not working totally against gravity. Yes?
I got an example of force.
Okay.
Look at this.
Okay, don't do that again. You might poke somebody's eye out if it goes crazy. But yes, you applied a force, you caused it to move, and then gravity pulled it down.
Yep.
Lots of forces at work, usually at once. Okay, here is our new stuff for today, and this is going to get to one of my favorite topics of this whole unit. So, we know that objects are going to fall because they're pulled down by gravity. We understand that, okay? That is not something new or exciting, I guess.
Nothing Newton about this.
Very funny. All right, so we also know at the same time there's air all around us here on Earth, right? And so typically that air is going to influence how things fall. And so the resistance that air places on moving objects we call air resistance. Resist means to kind of work against, right? So air is going to work against our motion. So air resistance is a special type of drag, because drag is when friction is working through a liquid or a gas, and obviously air is a gas. And so air resistance is just that special, very specific type of friction, okay? And the force of air resistance, because it's a friction, is going to work opposite the direction of motion. So if motion is downward, probably because of gravity, then we know that air resistance is going to work up. A lot of times this can specifically be called lift, like if you're using that effect, like to help with flight. So airplanes and birds, you know, all of those kites even, you have that idea that air resistance is, if you have a large surface area, you're going to try to use that to help lift the object. Even like parachutes, right, use that same kind of idea to work. And so the amount of air resistance is going to be directly related to the size and shape of the object. So if we want to increase surface area, because we want that lift, we want that kite to be lifted in the air, or we want that paper airplane to fly, we need to have those big wings. Yes?
Found the center of gravity on this eraser.
Yep, very good. All right, so we definitely are dealing with the idea that we can kind of manipulate the amount of surface area by changing the size or shape of something. So I have a little example. I have two sheets of paper, they're identical, and I'm going to crinkle one up. Right? So they have the same mass, but I've just changed their size and shape. If I drop these, which one is going to probably land first? Who thinks that the flat one? Who thinks that the crumpled one? Right? Right? You doesn't have to think too hard, right? It's pretty obvious. This has more surface area. You've increased the amount of space that the air can actually contact. Here you've reduced that. Okay, so if you're trying to make something more aerodynamic and make it go through the air easier and quicker, you want it to be, you know, more streamlined, smaller shape as possible, that kind of thing. This definitely is not very streamlined, right? It's going to catch a lot of that air as it's going down. Yes?
I made it more dense per square inch.
You did?
Because its shape is different.
Because you changed the volume.
It's no longer aerodynamic. It's not like a feather. A feather's flat, but if you crumpled up that feather, that would probably fall faster, so it's a different shape.
Well, kind of like this, right? This is, the feather's meant to catch air, right? That's kind of the reasoning behind the wings. Yes?
Wouldn't that paper go faster if you just like held it like this?
Well, let's see. If we can keep it that way, right? Same idea, right? You have drastically cut down the air resistance. Having it flat, I'm allowing it to catch all of that air. Yeah, very good point. And again, we're not changing the mass. It's just here the volumes are definitely different. So if you're talking about density, it does kind of relate to that a little bit as well. Okay, so if there's no air resistance present though, there's no air, then we should see that things fall at the same rate. And that's really hard for us to imagine because let's face it, we live in a world where there's air, thank goodness, or we would not be living very long, right? So I am going to stop my notes here and then pick them back up with a second video of notes because I want to show these two videos right now. They're pretty interesting.